Good morning, it's Charlie ZL2CTM. So just doing a part 2 video here looking at the second IF amp. That's the amp that's going to be sitting after the IF filter, the crystal filter that is, and that's going to be based around the MC1350 IF amplifier chip. So in terms of the actual configuration itself, this is what I'm pretty well going to settle on. Well, this is what I'm sort of trialing at the moment, more the point. And before I go any further, I was going to point this out here. All of this documentation here, including the code for the Arduino, etc., I all put up on the blogspot. So ZL2CTM at blogspot.com. If you go there, you'll find a series of blog entries, which are basically just scans of all this documentation. So there's no need to sort of try and take photographs off the screen. It's all sitting up there. So like I say, the MC1350 is the amplifier I'm looking to use. So just from a VCC point of view, just sort of sticking with the standard that I've been using from some other amps there. So 13.8 volts through a 100 ohm resistor, decoupled with 100 nanofarad and 100 microfarad, going into the VCC input. I'll talk about the input and output in a sec. Pin 5 is the variable gain port. So that's where you apply a variable voltage into here and you can set the overall gain of that device. As alluded to in the last video, I'm going to have two options for that. There's going to be a manual IF control, and then eventually AGC will come in through that isolating diode there, which will also help set the gain for that. The spec sheet talks about having that being fed via a 5.1 k ohm resistor, which we have there. And then this series of resistors I'll talk about in a sec when we get through the testing. The initial testing had 13.8 volts just through a 10 k ohm resistor directly to earth. And like I say, I'll talk about these two additional ones in due course. So in terms of I'll start off with the output, then I'll come back to the input. So the output, interesting enough, off the spec sheet it talks about an output admittance, admittance being 1 over impedance, of 4.4 micromhos. So if I was to look at, that's the real part, I'm ignoring the imaginary part at this stage. So 1 over 4.4 micromhos comes out at 227 kilo ohms across this differential output. So that's pretty high, and I note that a lot of the example circuits that use this device either up at 45 megahertz in the old televisions or down in say 455 kilohertz have tuned circuit outputs. So my assumption there is with a really high output impedance there, you're not dragging down dropping the Q too much of any tuned output tank circuit here. This arrangement here with the 12, 12 and 5 was the configuration used in EMRFD, and like I say, in the lack of anything else more definitive that I can find, I'll run with that one for the experiments. So that's 12 tunes here, 12 tunes there. So overall on the it's an FT37-43 with 24 tunes halfway through, a tap coming out, then continue winding on. So that was we'll call this the primary, and then the secondary was 5 tunes, which will go eventually to our mixer. On the input side of the house, so a couple of different options there. That seems to be pretty typical and described in the spec sheet. We've got the transformer, a coupling transformer in this arrangement, so across the two differential inputs, with pin 6 reference to ground via a 100 nanofarad capacitor, or a single-ended input here. So those are two different options. Now again, the spec sheet has a range of admittances at various frequencies. The closest frequency to 9 megahertz, which will be the IF for this radio, was 10.7 megs, and at that value there it was 0.36 millimhos. So 1 over 0.36 10 to the minus 3 gives us 2777. So that's the input impedance looking at the 1350. So my assumption here is I'm going to run with 500 ohms at this point here. So 500 ohms is the output impedance of, well, the real part of the impedance of the crystal filter. So I'm matching that 500 ohms up to 2777, which gives us an N of 2.35, square root of that divided by that. So there's a range of transformer ratios which will provide that: 3 to 10, 4 to 9, 6 to 14, etc. I'm going to run with 10 to 23 because that sort of gave me roughly the right amount of inductive reactance to get that approximately 4 times 500, ballpark figures there. So I'll run with that one, and that's quite durable with number 26 gauge on an FT37-43. So that's one to run with. Okay, so let's set that aside now and look at some experiments. So the configuration here is, if I can just zoom up a little bit, it looks a little bit ugly, but unfortunately that's just the way to get it all to fit on. So let me just, I think that's still in focus. So we have the input side on this side and the output over here. So there goes our 10 to 23 turn input transformer. It's a bit of a pain actually because the inputs are between pin 4 and 6, which are on opposite sides, and then the output's also on opposite sides. So unfortunately we have to have some little jumper leads there to make it all work for the type of circuit board I'm using here. It's not a printed circuit board, so to speak. And there goes our output transformer there. 24 turns tapped halfway, and now 5 turns secondary. The output, so on the output of that output transformer is a 51 ohm resistor, which will be acting as our load, and I'm scoping across that. The input, now the input here, if I just zoom out a little bit, in order to try and emulate the 500 ohm crystal filter for test purposes, I've got the output of the SIG-gen, which is 50 ohms, going through another 470 ohm resistor, and at that point there trying to get approximately 500 ohms, which we're scoping. The only other addition there for test purposes is this little switch, and that switch there is, if I was to go back to the circuit, if I can get down to here, is located right here, and it's providing either an earth or access to this variable attenuation here. So that switch is located right there. So that's what we see down here, and there goes that small 5.1 k ohm resistor that leads back into pin 5 of the 1350. So at the moment, if we were to flick that to that position, we are now earthing that 5 k ohm resistor to earth, and through the spec sheet that's the maximum gain position. And then flicking that back in again, and now that allows us to adjust the voltage being applied to that 5.1 k ohm resistor. So I wanted to run through a few tests here. So let me see if that's still visible. Let me just get that. Got a bit of a reflection there coming from the leg, unfortunately. Let's grab the intensity up a bit. So so what am I looking at here? So maximum gain. So at the moment, so if I was to look at the gain, at the moment they're on the same settings, and we can see there that if I use that variable or that pot, we get a huge amount of variation in gain there. By doing the maths at the input to the output, I'm getting a maximum gain of 25 dB. So that's with 13.8 volts on the VCC rail there, which is you know, I think about right. I don't know for sure, and I guess arguably once we put it into the circuit, if there's a need to add an additional amplifier, then so be it. We can always do that. So next one I want to look at was the max attenuation. So for that, the maximum voltage coming out is 1.4 volts. So I'm going to look at 1.4 volts divided by, or 20 log, the smallest amplitude versus the maximum amplitude. So if I was to come down here and then start cranking up the the vertical divisions and keep coming down, keep coming up. So there I'm on the maximum sensitivity here, which is 5 microvolts per division. So coming back here, you can just start to see it there. So look, for all intents and purposes, for a test point of view, let's run with 1 division or 5 millivolts. So 1.4 volts max, way up there somewhere, down to 5 millivolts gives us a dynamic range there, or a range of gain variation of around 49 dB. And if you were to go to sort of down to there somewhere, then you're in the realms of 54 dB, so minus 54 dB, which I think is probably quite respectable for, keep cranking that down, quite respectable for an IF amp there. So that's, yeah, it is what it is. That's pretty good. Saturation, which is another interesting one. So that there is at maximum gain, and if I was now to increase our input level, which we can see up here, you can see how there that the output is no longer increasing. So that was starting off at that's 0.6 volts coming in, and then cranking it up and up and up and up and up. We're up now to sort of 3 volts with no output variation there. Now I thought, oh, that might be of concern, but if my maths is correct, that's currently 0.6 volts coming in. To get to a point where I'm exceeding 0.6 volts from an arguably, let's say, a 1 microvolt input on the antenna, then I need to have 115 dB gain between the antenna and the input of this particular amplifier. Well, at the moment, I hope my maths is correct there, but at the moment I've got nowhere near that, of course. I've got 10 dB on the antenna ramp, I've got another 20 dB on the first IF, with a range of losses in between, with the bandpass filter, the mixer, the crystal filter will have some losses, as well as still debating about having that 3 or 6 dB pad between the first IF amp and the crystal filter. So I don't think this particular issue here is going to be an issue for the receiver. The next thing I want to look at was power gain. Power gain is interesting because that's what's quoted in the spec sheet. So if I was just to zoom back out of here again and look at some paperwork here. So power gain is 20 log V out over V in plus 10 log R in over R out. So just be careful there, it's the opposite. So that's power gain, and this is what's quoted in the spec sheet for the device. So just running down to our configuration, so 20 log 1.4 over 0.08 was roughly what I was getting for maximum gain there, plus 10 log 500 ohms over 50 for the output, comes out at 35 dB. The spec sheet was talking in the realms of, if I recall, power gain at 10 megahertz of 58. So yeah, I'm not quite sure what to think about that. You know, I guess at the end of the day the voltage gain seems to be there, so maybe just let sleeping dogs lie and leave it at that. Now the other thing I wanted to talk about was this voltage divider just here. So what I'm going to do, I'm going to try and zoom out here and include the screen and the meter. So we put the meter on volts DC. We can see there 5.9. Right. So let's come up to maximum gain, which is there. Maximum gain I'm looking at around, I can see there 6 volts roughly. Let's run with 6 volts, and then as we reduce the gain, so we're increasing the voltage. Now if I was to crank this right up again, and we'll say minimums around there for argument's sake, close enough, then we're looking at around 7 volts. So 7 volts, let's crank this right back down again, up to a maximum gain of around there, of 6. So a range of 1 volt, 6 to 7 volts. That's slightly different from the spec sheet. The spec sheet has a couple of volts required, but suffice to say I need to make some adjustments because at the moment the effective range from 6 to 7 volts only represents a small portion of, it's from there through to there. So as you can see, it's nowhere near from there all the way around to there. So what by introducing a couple of additional resistors there on either side of that 10k ohm pot, we can get an effective range from that intersection of those two resistors and the intersection of those two resistors of around 5.5 to 7.5 volts. So half a volt of slack on either side of 6 to 7 volts. So that's why I've introduced that 27k and the 22k ohm resistor there, just to allow it's not so sensitive when it comes to that particular pot. So I think that's all I wanted to cover off there. So at this stage of the game, I'll tidy this up. I'll probably have another stalk sticking up here with that pot hanging off it, including the 2 additional resistors. At the moment those resistors of course are not in the circuit. I'll take the switch out, solder things back up. I think in terms of input and output transformers, I'll leave these as is. The actual testing seems to be, you know, from an from a big hands point of view, seems to be about right. So I think at this stage of the game, I'll leave that as is. So in terms of carrying on with the project, I think next steps will be to again clean this all up, and we'll look to set it up as a superhet. So we'll introduce the crystal filter. I think at this stage of the game we won't have any kind of switching to allow the transmit and receive. We'll just set up purely as a receiver and then look to convert it to a transmit in due course. And I think, as was also pointed out, I am using an old version of Jason Mildrum's SI5351 library. It's sort of one of those things, once you've got a library and things work, I just store it away and I use it all the time. But I'm conscious that anybody who's thinking about doing this themselves and playing around with the code potentially will have some compiling errors. So I'll also look to pull in the latest library that Jason's put out and then make any modifications to the code to allow that to work. What will be interesting is, I think there was one comment yesterday just regarding having to comment out the correction factor to make this version of the code work with the new library. So it'll be interesting to see how that correction factor has been accommodated in the new library. But that's a different story. But suffice to say, we'll also look at updating that, and then of course, because it's now turning into a super heterodyne receiver, we'll have both coming out of clock 0 will be our variable frequency oscillator, which will go to the first mixer to produce our output of 9 megs, and then clock 2 over here, so maximum distance of separation there to try and minimize any interrelationships between the two, will be our beat frequency oscillator. So that'll be sitting sort of that 300 Hertz high of the 3 dB point of that crystal filter. But we'll cover that up in the next video or so. Anyway, I'll say 73 is there. If there's any corrections or anything I got wrong there, please sing out. Otherwise, we'll continue playing around with this radio. Okay, cheers all.